Hello, we are Team 23061 and our project is pressure sensing self-retaining retractors.
Hi, I'm Mackenzie Big and I'm biomedical engineering.
Hi, I'm Danya Perez and I'm also biomedical engineering.
Hi, I'm Evan Smith. I'm also biomedical engineering.
Hi, I'm Timur Shine. I am electrical and computer engineering.
Hi, I'm Mark Fawcett. I'm also biomedical engineering.
We have designed what we call the pressure system, which stands for Pressure Sensing Self-Retaining Retractor System, and will be referred to as such from now on. But why do we believe our project is so important? Unmonitored use of self-retaining retractors in the operating room could cause damage to the tissues at whatever incision is being held open. Surgeons infrequently monitor these retractors as they're dedicated to the more complex task of the surgery itself. Consequently, 10 to 40% of patients will experience chronic neuropathic post-operative pain from general procedures alone. This statistic should be alarming. A patient should not have to run the risk of leaving the operating room with a decreased quality of life. The pressure system aims to mitigate this risk by providing real-time pressure monitoring during surgery, utilizing an alarm to notify the surgical team if the pressure being exerted on the tissue by the retractor crosses the threshold of potential tissue damage, after which they can reposition the retractor accordingly. The system comes with an Android application that displays a real-time graphical representation of the exerted pressures, so the surgical team may reposition the retractor before this threshold is even crossed, if they so please. The pressure system removes the uncertainty from surgical retraction. Surgical teams can focus completely on their procedures with the faith that the pressure system will alert them of potentially damaging pressure exertion. In addition to making the surgeon's job easier and improving patient outcomes, the pressure system will also save and export pressure data in the form of a CSV file for subsequent analysis, propelling this field of operative research forward and offering surgeons the opportunity to be at the forefront of refining the system further as more data is collected and examined over time. The pressure system is divided into three sub-assemblies: the sensor, computer, and graphical user interface assemblies. The sensor assembly consists of two Flexiforce HT2L1 sensors, a Wheatlander retractor to which they are epoxied, and two steel plates on which the force sensors lay flat, all adhere to one another using Masterbond EP2HT2Med epoxy. The sensor assembly is the only sub-assembly that will be in the sterile field of the operating room, and all of its components are thus certified as biocompatible under the ISO 10993-5 standard of biological evaluation of medical devices for cytotoxicity. The computer assembly consists of an ESP32D board and the Flexiforce analog processing circuit. The computer assembly processes collected data after a raw signal is received and transmits the processed data to the graphical user interface, or GUI, system via Bluetooth. The GUI assembly consists of an Android application coded in Java via the MIT App Inventor and a Samsung Galaxy A7 Lite tablet for display of the application. Additionally, the GUI assembly encompasses the data processing after the raw signal is received, the transmission of the data to the GUI, the real-time display of data for the user, the alarm system to alert the user of high thresholds or durations, and the storage and export of collected data. The sensor subsystem was created through the union of the Wheatlander retractor, Flexiforce sensors, and fabricated steel plates from the AME machine shop using the heat-resistant, biocompatible Masterbond EP2HT2Med epoxy. This process involved the construction of a PCL holding boat, which was fashioned around the retractor tines, pre-fit with the steel plates to ensure tight setting of the epoxy and minimize spillage during the application process. The sensors were then laid onto the steel plate within the holding boat and left to set tightly. The process took several days to ensure maximal setting of the epoxy and the best adherence of the components, and was repeated for the other side of the retractors. For coding, we used the Arduino programming language to enable Bluetooth Low Energy on our ESP32, through which we were able to establish a connection between our Flexiforce analog processing circuit and our tablet. Since the Arduino Nano on our prototyping kit was not equipped with Bluetooth connectivity, we had to use another development board with wireless connections so that we would be able to transmit data to any tablet with our app. This process included figuring out how to power up the entire system with a single power source, and learning how to correctly connect pins between boards so that they could communicate with each other. The code itself, we used example code given within the ESP32, manipulating it accordingly to fit our needs. We first began with a simple blink test to confirm we could write to our device, and then proceeded to reading and displaying serial data from our force sensor attached to our prototyping kit. From there, we established a serial-to-serial connection from the Arduino Nano to the ESP32, and finally enabled the Bluetooth to our tablet with correct numerical values. The Bluetooth Low Energy is enabled in ESP32 by setting the ESP32 as the server and starting a service. After that, we specify the required parameters to be able to send the data. Afterwards, we started advertising our device for Bluetooth connection. The code in ESP32 computes the average value received over the serial connection in 1-second intervals for steady data presentation. This average is then converted to the force applied using a calibration curve that we created based on recommendations from the ASTM E74 standard for calibration and device testing. The force is then converted to the pressure and sent to the tablet over Bluetooth. The pressure system connects via Bluetooth Low Energy to a smartphone app that allows the user to monitor pressure levels throughout the surgery. The app allows the user to select a maximum allowed pressure level and emits a tone when that pressure has been exceeded, letting the user know to change the placement of the retractors in order to minimize unintentional tissue damage. Throughout the procedure, an easy-to-read graphical display shows the pressure readings in real time, updating the values for each side of the retractor every second. After the procedure is completed, the data collected can be saved and exported in CSV format, allowing data analysis through Excel, MATLAB, RStudio, and any other data analysis tools. The app itself was created using MIT App Inventor, a visual programming application that allows the development of fully functioning apps in Java language without the need for extensive programming knowledge. Through the MIT App Inventor, we were able to establish a secure connection to the Bluetooth Low Energy module on the ESP32, attached to the retractor system by identifying the correct MAC address associated with the ESP. Using the device address prevents the accidental pairing of a different Bluetooth device, and the Bluetooth Low Energy capability decreases the power consumption of the system and limits the heat produced by the circuitry. The pressure data is transmitted to the app already converted into the correct pressure units, so in the app, the only data processing is the creation of a list in the internal storage, and then the export of a compiled CSV file. The app can be downloaded on any Android device, including smartphones and tablets, and is easily shareable so the system is compatible with a wide range of devices. The calibration curves mentioned previously were created through initial testing with pork shoulder, an exceptional analog to human flesh. The curves, as can be seen, demonstrate an excellent linear relationship to which we can calibrate the device. We split our verification procedures into sections to which they collectively best correspond, namely the electrical interface, user interface, performance, and safety procedures. Our safety procedures were met easily thanks to our selection of silicone-coated wires for proper electrical insulation, as well as the consideration we took in selecting the materials that satisfied the ISO 10995 biological evaluation of medical devices standard for cytotoxicity. Both safety procedures ensure that the patient is not being put in harm's way through the introduction of cytotoxic materials into their body, as well as protecting the surgical teams using the system from electrical hazards. Performance durability remains to be completely established, though the 2 autoclave cycles we ran the system in did not damage any components, and the system as a whole maintained functionality. We are confident that the sensor assembly, the only sub-assembly that needs to be autoclaved after use, will survive the 3 consecutive cycles detailed in this requirement. Prior to testing our system prototype for precision and accuracy, we calibrated it according to the range of forces that we wish to detect, from 1.96 to 19.61 newtons. By nature of being force measuring sensors, the Flexiforce HT201 sensors we incorporate in our system are understood to satisfy the ASTM E74 standard practices for calibration and verification for force measuring instruments, another of our verification requirements. We demonstrated our system to be compatible with the Wheatlander retractor through our initial precision and accuracy tests on the pork shoulder, since it did not obstruct the field of view of the surgical site, nor did it impair the functionality of the retractor in any way. During these tests, we established that our system had a sampling rate of 22.2 Hz, more than satisfying our requirement that it samples the force at the retractor tissue interface at a frequency of 1 Hz. Our code will bring the sampling rate to 1 Hz as per our sponsor's wishes. We would like to thank our sponsor, Dr. David Margolis of Banner Orthopedics and Sports Medicine, for being so flexible and lenient in our design choices, as well as our mentor, Dr. Justin Hyatt, for providing valuable feedback when necessary. Thank you to Dr. Margolis' Orthopedic Research Lab as well for allowing us to use their facilities for our purposes.